This video is for topic 8, evaluating piecewise functions. We're going to focus on evaluating piecewise functions from a graph or from an equation. So what is a piecewise function? This is a graph of a piecewise function, and this is an equation for a piecewise function, and I like to reference them as being very similar to this guy, the Frankenstein monster. Yes, this is the Frankenstein monster. The story behind him is he has been stitched together by Dr. Frankenstein. That's why there's bolts in his neck. And these piecewise functions are very similarly, they are pieces of other functions that are stitched together to make a whole graph. So piecewise function is a function defined by multiple subfunctions, with each subfunction applying to a specific subinterval of the main domain. So let's take a little bit deeper look into how this equation turned into this graph. So here is our piecewise function, or our Frankenstein monster piecewise function. And looking at each of the individual pieces, we'll start off with the very top. This interval, if negative infinity, comma, negative 2, means that the input, if our x values are less than or equal to negative 2, then the output, our y values, will follow the rule 2x plus 6. So if our x values fall between negative infinity and negative 2, we're going to plug them into this expression 2x plus 6 and get a y value. So what that means is any value from negative infinity all the way up to negative 2, we're going to get y values that follow this rule, 2x plus 6. So the middle section, if negative 2 to 3, means that if the input, our x values, are greater than negative 2 and less than 3, then the output follows the rules of x squared, y equals x squared. And lastly, our bottom row, if our inputs are greater than 3 but less than infinity, then the outputs are equal to the rule y is equal to 2. So really what we're doing is we have 3 certain rules for 3 specific sections of the domain, and what that looks like graphically is I'm going to graph the function y equals 2x plus 6 in this yellow portion, or in this specific domain. I'm going to graph the function y equals x squared in this little section of the domain, and I'm going to graph the line y equals 2 only in this section of the domain. So let's start off with 2x plus 6. Here is the line y is equal to 2x plus 6. That's great if I graphed it over its domain negative infinity to positive infinity. However, I only want to graph it between negative infinity and negative 2. So what I'm going to do then is all this other graph that's outside, I'm simply just going to take and throw out. So this is the only piece of the graph that I really care about, because the piecewise function says only graph it from negative infinity to negative 2. Okay, let's move to the middle section. I want to graph the quadratic x squared between negative 2 and 3. Well, here's what the quadratic looks like over its entire domain, but I want to focus on between negative 2 and positive 3. So, just like before, I'm going to go ahead and take and throw out all these other pieces of the graph, leaving me with just this. Now, one note before we move on is notice there is holes in this particular graph. The reason we have holes is notice we have soft brackets, which means that I'm getting up and close to negative 2 and up and close to positive 3, but I'm not actually including those. If I was including those, I'd use a hard bracket and I'd use a solid dot. So we need to pay very, very, very close attention to the endpoints of our graph within each sub-function in sub-interval, letting us know whether we have an open dot or a closed dot. All right, lastly, between 3 to infinity, we're going to go ahead and graph the line y is equal to 2, but I only really care about it from 3 to positive infinity, so I'm going to throw off the remaining piece, and there we have it. We have our piecewise function graphed over the specific intervals specific to the domain. So that's how we got that graph. We're not going to be having you graph any piecewise functions in this particular, but we do need to be able to interpret between which section of a piecewise function we are referring to for this course and for the SAT. One of the most common SAT questions I see with piecewise functions is what we're going to be doing today. So let's go ahead and take a look at an example. Our first example is here. We're going to determine what the values are for certain x values in the piecewise function. So here is our piecewise function h of x. It's defined over 3 subintervals. And those subintervals are broken up by these specific domains: negative infinity to 0 with a hard bracket, 0 to 8, and 8 to infinity. So each question we're going to start off with is, what is h of negative 3? Now, this just means when x is equal to negative 3, what is our y value? Well, we have 3 different subfunctions to choose from: the yellow, the blue, or the green. Well, where does x equal negative 3 fall within these subdomains? That's right, it falls in the yellow region, or the top subfunction. So all we're going to do is take negative 3 and substitute it into this rule, x cubed. Negative 3 cubed, which is equal to negative 27. Okay, h of 9 means that x is equal to 9. And which subfunction does x equal 9 fall in with our domain? That's right, it falls into the green subfunction. Or another way to think about it is 9 falls in the subinterval between 8 and infinity. So all we're going to do is take this x is equal to 9 and substitute it in this expression, giving us 9 minus 1 times 9 plus 2, 8 times 11, which gives us 88. Now, the other way that this question can be asked is, instead of giving you the equation like we did with h of x, is I could give you the graph of the piecewise function and have you pull out the y values from the graph. So g of 3 means that x is equal to 3, and we need to determine where x equals 3 falls in with this graph. Is it in, we have 3 subregions here. We have the yellow portion of the graph, the light blue, and the green. Well, where is x is equal to 3? Well, x equals 3 on this vertical line. On the blue function, there's a hole at x is equal to 3, which means that we're interested in this solid dot at x equals 3 on our green function, or the far right subfunction. So when x is equal to 3, we come up here. Here's the point. That gives us a y value of 4. These are the 2 main ways that this will be asked on an SAT or on our quiz or test. Let's jump over to the left-hand side and give examples A, B, C, and D a try here. Pause the video for a moment and see if you can come up with the answers for this. Answers will appear in 3, 2, and 1. Here are the answers. Zooming in a bit. Example A, x is equal to 6 fell into the bottom equation. X is equal to negative 12 fell into the top equation. A little bit of math required there, giving us answers of negative 3 and 372. Example B, we don't have to use both pieces of the piecewise function here. X equals 7 and x equals 4 both fell into our bottom portion of the equation, giving us 29 and 17. Example C, here I gave you the equation and the graph. F of negative 3, looking at the graph, here's negative 3, the solid dot shows up at y equals 5. So we could plug it into the equation and get the same result. In example D, x is equal to 2 falls into the bottom equation again. Here's an example where a piecewise function doesn't jump around, don't have to have discontinuities. Here the graph just goes and flows into each other. There's a little bit of an overlap at x is equal to 2, but since it's in this bottom domain, we could substitute it in. And get 2 minus 6 gives us negative 4, or from the graph we can simply see it there. Okay. One last thing about graphs. Quick example here. If I asked you to pick which piecewise function worked with this equation, the key to doing these actually falls in the domain, whether or not we have open dots and closed dots, whether we're going to certain values. So here, if I'm looking at the top equation, we go from negative 6 to positive 3 included. So if I'm looking between negative 6 and positive 3, negative 6 and positive 3 on both graphs, I should see the endpoints being included on both of these. Well, unfortunately, in this graph, we see that there's an open dot versus here where there is a closed dot, meaning that answer B is going to be our graph. these ones on the SAT show up. It's usually just about whether the endpoints are included or not, or whether they even go to where the endpoints or the domain says they are listed. So jumping over quickly to our other two examples, take a moment and see if you can get these. I'll show you an answer here in 3, 2, 1. First example, f of x, it was a. We needed 2 hard brackets or 2 solid dots on our first subinterval. This one had a solid and an open. And then for h of x, the interval goes from -6 to 4. Here it stretches from -8 to 4. We actually want it to be -6 to 4, so answer choice B. So what I need you to do now is hop on to Khan Academy and go to your assignments. We're going to try evaluating piecewise functions. There are 4 problems for you to do. When you finish those, I'll give you the next piece.